So the next portion of the lecture is about the D latch. So what is the D latch? So first off, no, in your 140 class, you won't be doing this until the latter half of the semester, but you will be discussing logic circuits. No, so logic is kind of nowadays not really that exciting. No, to make computers, to make everything that is useful, that is digital. No, we need memory. No, so a simple memory element is made using two inverters, which we have been talking about so far, right? So memory, we need to have a circuit that can keep a 1 or a 0. That's a digital signal, no? Now, we observe that if we interconnect two inverters in a positive feedback, no, we're able to store information. So, for example, here, if this wire is 1, then this inverter will turn that wire into a 0. But then this is now a positive feedback. No, it's stable at that state because this inverter turns this into 0 and this inverter turns this into 1. No? But it can also be vice versa. If this wire starts at 0, no? This wire starts at 0, then this inverter will enforce that this is 1. But then this inverter will enforce this to be 0. So it's like a circuit that has two stable states. And if we choose just one side, we say this side is the one we like, then there's two states to this circuit. It's either in a 0 state or in a 1 state. No? And this basic principle is what we call a latch. And this is the most basic memory element. Okay? So, how does a cross-coupled inverter work? How do we start analyzing this? Well, to explain the behavior, we can just overlay the voltage transfer curve of both inverters. So here, no, we have the voltage transfer curve of a normal inverter, and then when you switch the output and input around, you get another voltage transfer curve, which is like this, right? So overlaying both, because really this is the same graph, then we find that there are two stable states, no? Because these are the only allowable states. Remember, uh, a circuit has to follow the intersection of all the rules around itself, no? And the intersections are these ones, no? But note, C is known as a metastable state. Why is that? So let's try to put the circuit in a specific starting condition. So let's say we start here, no? That is, this is the output of 1, right? And this is the output of 1 and input of 2, no? So if it's the input of the circuit 2, then it will result in a Vout 2, which is here, right? So then, okay, if this is the output 2, then that's the input of 1. So then the next output of 1 would be here, and so on, leading us to point A, right? Now, let's say, okay, another case, we start here, okay? Okay, so this is the input of 2. So then, the VTC of 2 will be here. So then the output of 2 is now here, which is the input of 1, which puts us here, and then eventually puts us at point B. No? Note, they all kind of are attracted to A or B, not C. So what happens? C is technically an intersection. It is allowable, but if you add a little bit of noise, you're immediately pulled towards A or B. No? So C is known as a metastable state. No? So you can visualize that by a ball on top of a hill, which can roll towards A or B, but it can be balanced right on top at C, but it's very difficult to do that. So, skipping that. So, for us to make practical use of the cross-coupled inverter as a memory device, we need a way to make sure to put in a known state into the device. So to make it like that, we need something called a D-latch. If we add switches to the circuit, we can we can put in an input to the cross-coupled inverters. So if clock is 0, for example, it just remains the normal cross-coupled inverters. That is, it keeps the state. Then okay, at clock equals 1, no, we break the cross-coupled feedback and we put in whatever we want as the input D. So for example, if D was 1, then this turns into 1, this turns into 0. No? So then what happens in the next clock cycle? If clock turns 0 again, what happens? This is left at 1, this is left at 0. Now the circuit remembers what we put in. Right? So let's say, for example, in clock equals 1, we put in 0, this turns 0, this turns 1. So then, when clock turns 0 again, this remembers that this was 1, this remembers that this was 0. No? This is the basic principle of the D latch. No? So as an example, observe here. So for example, clock was 0. So then, okay, if clock is 0 and Q was 0, then it's at 0, 1. Right? Then, okay, D goes up to 1, but it's disconnected, so we don't care, right? And then clock goes to 1. So what happens? D is 1, which is copied by this, no? And then Q prime turns into 0, which turns Q into 1, no? And then after, so this turns into Q, right? This turns Q into the same as D. And then when D went off, no, went down, then Q also followed it and went down, no? And then finally, when clock went back down to 0, Q keeps the state regardless of whether or not D actually changes, no? So yeah. So with that, that's the fourth part of lecture 1.